Okay. I have myself, like the speaker is on loud, so if you guys can't hear or have any issues, just let me know. So the paper today that I'm presenting is called Meta Continual Learning Revisited, Implicitly Enhancing Online Hessian Approximations via Variance Reduction. So very technical title. It's combining like meta learning with continual learning, and then talking about using a Hessian to do variance reduction. The technique they use in the end is actually quite simple. Like I was wondering if they might have even been a little bit disappointed with that was like what was worked. But this paper is one of the best papers at ICLR this year, and what they do is they're able to do some cool math, which I'm not going to get too far into, to give some theoretical guarantees around the technique that they use. And I think that's one of the reasons why this is a good paper, because it basically connects two methods for doing continual learning under like a unified framework, and then shows how their proposed technique improves on all existing methods that use this framework. It's not the only way you can do continual learning. I'm going to go into some depth about this way of doing it, and it's actually this way of thinking about it, but there's other ways. That wasn't, I mean, at first I thought they were creating a unified framework for continual learning, but they're actually just doing it like a unified framework for methods that think about this in terms of Hessian approximation. So before I do whiteboard stuff, I want to show you guys this. So I'll just highlight the paragraph with my cursor real quick. This part, that's what I want, just so we have some context. So the problem setting of continual learning is that you have multiple tasks that you want to use the same model to accomplish in series. They have two different settings in experiments which they use. One is, say you're just like online being fed small amounts of data, where there's also probably distribution shifts, so you're like not always seeing the same type of data. And so you're just given one batch at a time. That's one way. That's one area where this method can be used. And the other one is you're given like the full amount of data for all of your different tasks, but you're not told which task you're going to be accomplishing when you're being tested. So it could be any of the tasks you've seen so far. But anyway, you have this sequence of tasks, and for each task you have n to the superscript I samples, which are pairs of like input-output pairs. So you have like a feature vector and then some target. I don't think a lot of the math would change for multiple targets, but anyway. So that's the first thing that I wanted to say. And then I highlighted in red. So you're trying to train a parameterized model with models theta. And as they say here, the objective of continuous learning is to minimize the empirical risk of all seen tasks. And what that is that they have a loss function, which is in terms of theta. So I think they're like, the way they're doing this, they're assuming I'm marginalizing over the data set that I have as an approximation for the task. And so this is like my theta over the entire task. And so you're saying like, okay, I want the average of the losses for all these different tasks to be as high as low as possible. And so the big thing about the setting of continual learning is that makes this a big component of this problem is this idea that every time you're working on a new task or you're drip fed new data, you don't have access to the data beforehand. So unless maybe they kind of do, because the technique they use actually uses a memory buffer. But anyway, let's kind of assume that you don't have access, or you don't want to have access to the full data set because this method wouldn't scale. That's kind of like how can we use as little previous data as possible while still maintaining good performance on those tasks? And so the the key idea behind this whole paper is equation 1 here. So they give you the setting of they tell you, okay, actually before we look at equation 1, let's just look here as an example. So they're saying, okay, to calculate this empirical risk in the setting where you only have 2 tasks, what you really want to do is you want to calculate like L2 and L1, where L1 is the empirical risk of the first task and L2 is the second task, but we can't calculate L1. That's the big idea. So instead, we have to come up with some proxy for it. And that's what they're saying here. So like for this 2-task setting, we need to take into account this proxy. So then they're like, okay, let's use a Taylor approximation of this proxy. And I will explain that, but I wanted to do a little bit of a background on Taylor series. I'm just trying this out. If you guys don't like this idea of doing a review of some math, again. But I thought it could be cool. So now I'm going to talk a little bit about Taylor series and Taylor series approximations. Hopefully you find it interesting. So I'll stop presenting and hope that the people online can see the board. Okay. So I wanted to go over like the fundamentals of this idea. And there's the basic idea is you may have some, I'll move out of the way because I wish I should have done it this way because I'm left-handed, but if you have some function that you can represent as what's called like a convergent power series, which is actually, sorry, this would, x. It would be a to n is equal to x minus a power n or so say you have a function that can be represented in this form. So you have an infinite sum of basically polynomials with scalar coefficients. Say you set x to, or you set a to 0. So the difference between these two, it's, say that you set, let's look this up. This should equal 1, right?
Alpha.
Yeah. Say you set alpha to 0. So you set alpha to 0, and then you set I forget what the derivation is. Something along the line. You set alpha to 0, and that should be just x to I.
All terms disappear, right?
What?
All terms disappear when
alpha is 0. No, because you set.
Oh, sorry. You set x to alpha.
Oh yeah, sorry. Set x to alpha. If you set x to alpha, thank you, Arvid. Then all terms disappear except for the first term. So that means that f of alpha is equal to a to the 0. And then say you take the derivative of this first term. So f of x is equal to sum from I equals 0 to infinity, or from 1 to infinity, a to the n divided by I x minus a. So if you do that, so this is just taking the derivative on both sides. I might 1. Then you take you do the same thing. You set x to alpha. Then what you're going to get is that f of x is equal to a to the n divided by 1. Sorry, a to the 1 divided by 1. So basically, this is the first couple of steps, but what you can show is like if you can represent a series, a function in this way, then the coefficients of this function a to the n is equal to f of x, x of a divided by n factorial. And that's what a Taylor series is. Sorry, this is the number of times that you have to differentiate. So like a to the 0 is just f of a divided by 1. The second coefficient is a to the 1, which is the first derivative at a divided by 1. The second one is the second derivative at a divided by 2, and so on. And what that does is that provides you with a way of approximating a function. Now, what I find cool is this doesn't work all the time. For some functions, you can't approximate at least either parts of it or the whole thing with the Taylor series. But there's some functions where this works for like the entire domain. So from minus infinity to infinity, like sine or cosine, or which is just kind of mind blowing to me because you're representing f of x at one point in all of its derivatives, and you can get anything in the entire. But anyway, what's also true is that you can, I think for a lot more functions, you can approximate locally the function, like what it is within a certain area, and also have like a bound on how much error there is within that area, depending on making certain assumptions. So let's write out the Taylor series for this in up to the second term. So it'd be f of a plus 1. Oh, I forgot the. Okay, so these are the first three terms of the Taylor series, and these terms are used like this is used like everywhere. Like this is used to derive most of the theorems in calculus. It's like a really important theorem. That's why I decided to read a little bit more about it, because I've seen it in other places. Like I've been reading about diffusion and how they calculate integrals of stochastic functions, and they use this approximation to figure out how to do it, because with stochastic functions, they're actually not differentiable anywhere. Like so what that means is that you can't use all of this theory that you usually use. You have to use something else. So anyway, this is the Taylor approximation of this function at this point. And what's interesting is that you can actually, and this is what Taylor showed, but actually Taylor showed this in the 1700s, but Newton actually kind of figured this out in the 1600s. And there's some people, like before that even, there's some Indian mathematicians who kind of figured out approximation, like the other series that are similar to this, even in like the 1400s. And it's just crazy to me that they figured this out if you learn about the math of this. But anyway, so that there's a bound where, so say this term over here after the second derivative is the remainder term. It's something like this. Then what Taylor showed is that you can approximate this term is less than that, where this is to the third power, but it could also be like to the n. Yeah.
So, no, does it count it through?
Oh yeah, sorry. This would be 3 factorial.
But this must be But for some class of functions, right? It's just,
Yeah. There's always, or I think it's always like, this is true if the function is like within a neighborhood where it's completely smooth, and some other things as well. Not only does it have to be smooth, it has to be other things as well.
And
sorry.
where is the remainder comes from?
From the additional terms. So remember how this goes from 0 to infinity.
Mm-hmm.
So I just put the first 3 terms, but there's another like infinite number of terms that add to it.
Oh.
Yeah.
I can ask a question. Is this in here? So this is alpha subscripting or
Yeah.
power?
Should be I.
Oh,
right?
so this should be I.
Yeah.
Oh, okay.
We said that I think you could easily have like a 1 over x hold somewhere on those lines as well. That would still hold, but as long as you don't get too close to the hole. But then the I think that there's some restriction on the alpha I have to fall off quickly. The alpha i's have to fall off in a certain power law. I think more than 1 over x. Right? If it's only thought of as 1 over I. With thought of as only 1 over I think it becomes logarithmically divergent. So they have to be faster.
Yeah, R has to be convergent series. You mean R has to be a convergent series?
Yes. Yeah. Or F,
Well, it's
yeah.
bounded by convergent series.
Yeah.
Which is how you get the bound, right?
Which makes it this very funny that there's no factor in front of the x minus alpha to a certain power.
Yeah, I have to. So actually, let me read. You're right. There should be a factor because I simplified it too much. This is little o notation actually. So you can take this away too. It's little o notation, which means that the remainder grows much slower than this does. That's the true bound.
Yeah.
So this is always multiplied by some number larger than this. But anyway, so like I said, this Taylor series is like a fundamental element of everything that we like. So much parts of what we do. It's underlying a lot of stuff, and so it's also underlying what's going on here. So now we can go back to the paper. Let's go back to the paper. I'm just checking if there's a question. Okay, so if we look at equation 1 at the bottom of page 2, what they're saying is like, okay, we don't want to have to recalculate L1 every time we are training on a new task. So instead, we'll create some kind of approximation for it. And the approximation that they use is a Taylor approximation. So it's the loss at the original model parameter. So after you train task 1 or task 2, it'd be the parameters at that point, the difference between the parameters times the gradient at that point, and then like the Hessian, the Hessian is like a matrix of or like the second derivative, but when you have multiple inputs to your function instead of just one squared. And so they argue the first term A does not have any it doesn't have any impact on theta, like the current terms, because it's not in theta. Theta isn't there. Like theta hat is there, but that's the original parameters, not the current parameters. So we can ignore that. And then they say, which is a bit of a strong assumption, and yet for me, as you go further and further away from theta, that like no, sorry, it's not a strong assumption, my bad. But they're saying like this parameter should be near 0. This term should be 0. B should be 0 because the model should have converged in its trading. So the gradients at that point, you should have found a local minima, which means that your gradients at that point are 0. So this is 0. So really the important term to approximate to make sure that you're approximating the function is the Hessian. You know what the Hessian is, and you can calculate this.
So we do assume that we have fully trained the model at
each task.
Yeah.
And so then what they do is that they talk about, there's two methods that they look at here. One is regularization methods, and the other one is meta-learning methods, which we'll talk about in a second. But for regularization methods, they basically say, if you look at equation 2, that like some assumptions, and if you use the assumptions and you're using the regularization methods that have to do with the Hessian, then this is how you update your model parameters. And if you look at what it's saying, is that usually when you're doing stochastic gradient descent without regularization, this whole matrix with all of the Hessians in it would be just an identity matrix. So you're just saying like, okay, I'm taking the gradient with respect to my loss, and then I'm minimizing that by taking a negative step with an alpha as your learning rate. But now what they're saying is we're going to multiply the gradients by the sum of the Hessians for all of the inverse of the sum of the Hessians for all of the other of all of the previous tasks. And their argument here is that, and someone who knows more about linear algebra can help me with this. You guys, I think, know a lot about linear algebra. I don't really either. But so their argument is that the Hessian describes, I guess, like they're saying it describes curvature, and there's like directions of curvature. And so the directions of large curvature are, I guess, those are areas where it's not where there's large changes. It's not a gradient, it's a second derivative. But okay, I'll just explain it and then you guys can help me, which is that you don't want the model to change like the model parameters in directions of large curvature, because those are the directions in which the model has like learned how to classify for the previous task. You want it to, I'll go look at the question in a second. You want it to change in the areas of small curvature because those are areas where the model has maybe some more capacity to learn how to classify the new task without having to, without sacrificing its capacity on the older tasks, on the other tasks. So that's their argument for what's going on here, why this is the objective and why this is a good continual. Yeah, go ahead.
Is the argument about the Taylor approximation, or is it about the original function?
I'm just seeing it. Okay. Say that again.
Is the argument about the original function, or maybe it doesn't matter actually? So do we still hold the assumption that the Taylor approximation has only the first 3 terms, right?
Yeah.
Only the quadratic term.
Yeah. But they're saying, okay, this is a good approximation of the function. As long as we are able to like keep this true, then I think it's kind of trying to maintain that maybe that the Hessian matrix doesn't change that much for when you're training on new tasks.
Or at least the theta knot around which you do the perturbation. But if you have your H1, H2, Hn, they are technically on approximations at different parts of your parameter space. And if you move very far away from it, then that should break down. So I don't know, but it looks like you sort of have to assume that, yeah, as I said, the Hessians sort of the curvature overall doesn't change too much
with respect to the original task. Yeah.
I was going to say, the way I was just thinking of it is, imagine if you're in a steep valley that is changing, so the second order derivative changes, it's not a circle. And then, but it's in this direction, it's steep, but in this another direction that it isn't, you only want to perturb the direction that it isn't. So you want to move in those directions, and that's why we're looking for small.
Yeah, that's a good point. I like
small. Otherwise, I'm climbing up away from my minimum.
They therefore get too bad on the original task.
Yeah.
Can you not make the same argument also about the gradient, not just the Hessian?
I think they're saying like the gradient is 0, so we can't. But yeah, you probably could.
The difference, I think, is that with the gradient, once changing from towards the gradient direction won't make that big a difference. But if you use the Hessian to move, it will make a much bigger change to the model. I think.
And it actually would the gradient equal zero assumption, wouldn't it even be better if we put it back in there and have the gradient term as well? Because then, because I would argue that the moment I move away from the theta not just the boundary term, which seemingly happens, right? Because that's what the gradient moves on. Then, well, yes, at that point, the Hessian is biggest, but the moment I move away, the gradient is potentially much easily the stronger factor.
But I think one of the assumptions that they make throughout this is that the gradients stay at zero or are
Okay,
near
yes.
zero. But
Yeah.
that's true. That's an assumption that could break.
And I think you can probably estimate sort of like because the Hessian has a size, your gradient parameter at zero has a size, but it's only. No, I'm saying. Sorry, no, I think I'm saying wrong.
Okay, so this
Yeah,
kind of
understood.
update step is the update step, which is what they're focusing on throughout. They want to show like, okay, we're making this approximation of the function, and the way that we make sure that this approximation holds and basically this loss function stays at where it is by incorporating the Hessian in the update like this. And it's more they're showing that for all the different methods that think about continual learning in terms of this Hessian, if you can show that this is what the update looks like, what the update is mathematically, then you're doing that. You're making that approximation correctly.
If you think about the Hessian second order derivative multiplied by the gradient, you get something like a first order derivative. That is the approximation to the first order derivative as you move away
Yeah.
for each task. I think that sort of works.
But so for regularization-based methods, what they do is at the end of training on each task, they calculate the Hessian, or maybe as they're doing it, but yeah, they calculate the Hessian, and then they save it, they fix it, and they use that. But the problem in what they're arguing is that like since your model parameters change, it's actually much more useful to have like an up-to-date version of the Hessian, like that take into account where the current parameters are. So when you're updating it, you're still like you're basically updating the model in like the right directions of curvature still. And so this is kind of just going over the regularization-based methods, but then they talk about the meta-continual learning-based methods, which I'll go over now. Next page. Oh, what am I doing? I see my cursor. All right. I'm stuck.
Do you want to close the full screen?
You think that's why it's not letting me? Maybe. How did I get to this one then? You. Okay. We talked about that. Okay. Now I'm at a continual. Okay. So.
Are you still sharing the screen?
Yeah.
Okay.
So I'm a little bit cognizant of time. So, but I'll go through this, and then I'm just going to go through the results. I'll go through and also the method that they suggest. So first, I'll explain to you how meta-continual learning works quickly, and then we'll look at the update step. But we won't go into too much of the math. So the way meta-continual learning works is that you have what they call like a memory buffer for each task. You save a certain number of examples of each task as you go through them, and then what you do is you just when you're what do you do? So at each step of training, you have your model with parameters theta, and you sample from the memory buffer. You take the current parameters and you minimize the loss with respect to that task. And then you do that for as many tasks as you've seen so far. Like tasks. And you get a new set of parameters, which are, they're called theta k. So you start with parameters theta, then you get to parameters theta k, and then you get your batch from your current data set, calculate the loss with respect to that, and then you calculate the parameters, you calculate the gradient with respect to the original parameters. So not with you're using the updated parameters to calculate the loss here, but you're calculating them with respect to the original parameters. So you're taking a derivative of a derivative because you've performed gradient descent in the previous step. And in that way, you calculate and they basically what they show, actually it's a proposition, but with if you make these assumptions and this is true, they're saying that you have the exact same type of update of the original parameters, which is that you have some Hessian, which describes the directions that you want to move in or not move in, and it's taken into account in the update function. So that's how meta-continual learning relates to this Hessian update. But what they say is that, actually, this Hessian update is this update here, the way that continual learning is done, has a really high variance because you're probably using a very small subset of the data in your memory buffer. Otherwise, it doesn't even make sense to use the memory buffer. Because if it's so big, then it defeats the purpose of the task we're trying to accomplish. And so they say, so how can we get a lower variance estimate of this? And what they suggest is a momentum term. So like I said to you over here, what you do is you start with your parameters theta, or theta b here. Then you get to theta bk, and then that's when you get your batch from your original data set, from your current task, and you update it. You calculate your loss and you calculate your gradients. So this g epsilon theta b, this is your gradients with respect to your original parameters, but with the new parameters on the batch of the current task. And so they perform momentum on that gradient that they calculate. That's the main idea here, is that by performing momentum, taking into account the previous task, that you actually get a lower variance method. Yeah. Okay, that didn't take that long. Now, oh, cool. And then again, lots of math, which just shows that the update is the same. You're using a different Hessian though, because it's one where you have momentum. They give you a little bit of properties of that. But then what they can do with quite a few assumptions about the function and the landscape and everything is they can create a regret bound on this method. So
That's the question.
Yeah.
Is it the Hessian inverse?
Yeah, it's the Hessian inverted.
Right. Is it practical?
Well, okay, that was something that I was wondering this whole time, because I was because this is the Hessian with respect to all the parameters in the model.
Yeah.
So that means that if it's an LLM, then it's a billion by billion or tens of billions by tens of billions matrix.
If you can invert the Hessian, you don't need gradient descent or add them or anything like that.
The inversion is probably still
you can't invert
relatively easy part, but calculating the Hessian in the first place is.
Yeah, so you can't invert it. It's it's cubic in terms of in dimension. So its memory will blow. It will take more than time of the universe or whatever.
Mm-hmm. They do for the networks they use. They obviously can do it, but I don't know how scalable it is.
You can approximate. Maybe they use approximation.
Yeah, they do. Sorry, they do use approximations. The regularization methods that they used before use the Fisher diagonal approximation.
Yeah.
And then the one that I think they're working off of uses the Kronecker, Kronecker something approximation. So the Kronecker one has off diagonal terms and the Fisher one has diagonal terms. But then on top of doing that approximation to calculate this, they also use momentum to calculate their Hessian instead of just using the gradients, which means that you have a different Hessian.
on that.
Yeah.
I guess you don't need very good approximations, and it's a small model probably. So it's okay.
Didn't they? We were talking about the Taylor series before. Aren't they using the Taylor series to build the estimate of the Hessian?
No, the Hessian is a part of the Taylor series, so you have to have it in order to do the approximation with the Taylor series.
Of course.
Yeah.
Okay.
But yeah, they are using an approximation. That was a good question. I was still thinking these matrices are huge because you have anyway. But
Maybe
anyway,
they're sparse.
yeah, they're very sparse.
If they're very sparse, then maybe
Would they be generally sparse?
But probably not in reality, but the approximations that they use are sparse.
Yeah.
Like I said, the first couple of methods that looked at the Hessian that were regularization based used this Fisher information matrix to approximate the Hessian, which is a diagonal matrix. So they just have to have one term per parameter. But there's other ones that have often diagonals. I actually see this methodology a lot in research of I'll come up with like a more computationally expensive but provably better method. And then when I do the results, I get better results. But then you have to question what we're talking about. Like, is this a computationally efficient? I think the improvement that they suggest really isn't that big of a deal, but you do have to store like the previous gradients in order to do it. Oh, actually, sorry. One thing to say is that for these meta learning based methods, they don't actually explicitly calculate the Hessian because they are calculating hypergradients, so like gradients after gradients. But I don't know if that means that it's less if they're like calculating the Hessian somehow. Like, I don't know if when they're calculating gradients, they're having to calculate one gradient per parameter, or if they have to calculate like many gradients per parameter because of the fact that they are taking the gradient of a gradient.
Also, if the Hessian, you take the inverse, right? So wouldn't that slow down training quite a bit?
So for all of these results, they're not saying this is how you update the model. They're saying this is equivalent to how you update the model.
Yeah.
So it might be the case. I mean, for the regularization-based methods, I think it is actually how you update the model. But for these meta-learning methods, I don't actually think they're inverting the Hessian. They're just like doing normal gradient.
But I mean, the gradient is gradient of the loss time times alpha, right? But now 1 over the Hessian is the sum of Hessian, right?
Sure.
And so let's say they have some volume to them, right? So then this goes 1 over the sum of the Hessian. I don't know how that scales, but I could imagine that really drastically might reduce the gradient period, right? Because if it's diagonal, it must go as the weakest gradient squared times n essentially, right? So yeah, you slow down.
Yeah, that's probably true too. Yeah, there's a lot to unpack here. Then they have a lot of results in the appendix, but I'll go through some of the results now. I think that just to highlight it, this result is a pretty big one because they have like a regret bound in terms of continuous learning. So I think that and supposedly this is like the optimal regret bound you can have in continuous learning. So they're proving that they have that, but it's under like a huge number of assumptions, which I think are hard to hold. Like, I was wondering to myself, do most neural networks have a continuously smooth loss landscape? I have no idea.
Locally, maybe, but if you have
Technically, yes, but
Okay, actually, I have to. So they perform experiments on 3 data sets: sequence CFAR10, sequence CFAR100, and sequence tiny ImageNet. And so For sequence CFAR10, you have 5 tasks where you have it's a 2-class classification task each time, and you should see them in sequence. For sequence CFAR100, it's 10 tasks, each with 10 classes. So harder one. And then sequence Tiny ImageNet includes 20 tasks, each comprising 10 classes. So probably even harder. You could say this one is even harder. And they compare their method to a ton of different continual learning methods. One thing they do is that they actually implement each of them and train the models, which I actually like. Personally, I like when researchers just take the results from the paper. But maybe I don't know, maybe they didn't have them for this or something like that. But they have two metrics that they use to calculate performance. One is overall, what I would call like overall or average accuracy. It's like the average accuracy over all the tasks of classification. And the other one is the accuracy of the latest task. So the one that you've trained on last. So I guess the last one. And you can see that this is a table with one of the results. And the reason why there's a line from the bottom 4 and the top is that the bottom 5 all use some Hessian approximation in some way or another. And then all these other ones are other ways of doing continuous learning. One thing I found interesting is how low, like this is state of the art, and how low these accuracies are. So like for these tasks, your average accuracy is like 30% or 20%. And if you think about CFAR sequence 10, that's like worse than random. There's something, because there's only 2 classes to guess between. Oh no, that's why, sorry, that's not worse than random. They're better than random. But you can see like these numbers are not that high in comparison with the numbers you get for CFAR 10 or CFAR 100. That's just an observation. And so they use these results to answer a couple of questions. The first one, yeah, I'm listening.
Maybe the term regret. What is the benchmark for the regret with respect to what is the idea? Could it be if I train the all of data and all tasks at the same time and then some and then everything increases that?
So I know regret from reinforcement learning, and a regret from reinforcement learning is
often you would have not chosen the best action.
Yeah, or yeah, what's the difference between you choosing the best? Yeah, how often you wouldn't choose the best action? So it must be like, but I think it takes into account what you know at the time, because you have a certain amount of information at that time, and it's like how if you had absorbed all that information and you could make a good decision, like decision based on that, how good would that decision be versus the one you actually make?
I mean, there you often know the true model, right? But here, what is the correct answer is, or the correct theta must be like trained on everything.
Yeah.
Or trained on all samples up till the ones that you've seen.
Trained at the same time.
Yeah.
You're not going to retrain another model just because you've got another mini bank.
But because it seems the data sets, the tests on it are so large that you can't do the benchmark test, so you actually can possibly train it on all of them together, which might be interesting because you can sort of probe how good these assumptions perhaps are.
But I do think like maybe we'll do a paper on regret. I've always kind of shied away from that because when I was studying it and I met people who were doing research on this, it was like incredibly theoretical, like way more theoretical than like my background or anything like that. But we should I should at least know what they mean by that. So sorry, I can't give a better explanation. Okay, so they ask a couple of questions about like this is what they're saying, like this is what we want to show with our results. They say, how does their method perform against other methods in online continuous learning? And they say ours is the best. That's why it's bold. Well, one thing that I was like, the difference between these performances isn't that huge in my opinion. I mean, with respect to all the other methods that use a Hessian, it is. But if you look at these, actually this one's better. Like these, so the plus or minus is a 95% confidence interval. So their method is the highest average, but the confidence intervals are within each other. So I still think it's a good result, and that they should, like, this is definitely like an interesting paper that provides a lot of improvement, because it's taking up one way of doing continuous learning and just like really making better results. But in terms of is it actually state of the art, it's like a maybe for me in terms of like the statistics of the results. But they do show, okay, our average performance is higher than everyone else's. And then the second question is, how does their method perform as you vary the memory buffer? So this is the number of previous examples you say for every task. And obviously, as I actually thought this is kind of a trivial result. Maybe they have to show it. Like as you increase the memory buffer, the performance increases. Makes sense to me. Again, there are some methods that are closer to theirs. They're pretty close. There's more here than here. How effective is their method in dealing with increasing non-stationarity? So this is like, maybe there's a class imbalance in one of the data sets, or many of the data sets. That's what they're talking about, non-stationarity. And so they model this by randomly changing the class distribution, either in a random way or in a linear way as they go through the tasks. And they see that their method outperforms all the other methods. You can see it over here. That as like with all these different methods of changing making the task non-stationary, they have the best results. These ones don't have confidence bounds. Maybe they didn't have enough time for it. Anyway.
So the order of the tasks does matter, right?
In theory, it probably does, based on like how similar they are, something like that.
So you wouldn't be able to forget at some point, right? So that is, because some problems like on you won't forget at some point very old samples, so they get old.
Unless you're going to be tested on it.
Yeah,
true. So it depends on the situation. Okay, we talked about that. Whether the proposed method is still effective, this is question 4, using different backbones. So they did the same, they've been using like an inception network for all of these experiments, and they did one with this smaller network that's called PCCNN, and a memory buffer of 200, and they get the best results there. So again, they say like, okay, so we can generalize across networks. They did that. I bet that I could totally see that being a reviewer comment, that they were like, you need to train this on many different on different architectures. And then how does their method compare to other variance reduction methods? So they so the whole point of their method is that it reduces the variance in the Hessian approximation. And so they compare it to, one is they increase the batch size of the replay. So like of the batch size that they extract from the memory buffer each time. And 2 is they use momentum on SGD. And what you can see is that the momentum on SGD doesn't really help that much. But if you increase the batch size, it's equivalent to their using momentum, which makes sense. Because the whole point is that like the reason why there's variance is because there's variance due to the fact that like the batch isn't representative of the overall data set. So if you increase the batch size, it should be more representative of the overall data set. And then the last one is just showing like, does this actually reduce the variance of gradients? And then they have like another meta learning method and their method, and they showed that like our line is below the other line, and this is the relative gradient variance. So they're showing that their gradient has less variance. And yeah, that's the paper sped through pretty quickly. Lots of math, but I thought the original idea was I like the original idea of using a Taylor approximation, thinking of it in terms of the Hessian. So yeah, that's the paper. Another way of looking at continual learning. There was actually another paper I was debating on presenting instead of this, because all of this continual learning stuff, it's one side of the problem of where this really could be used. The other side is like deciding what data to train on. Because, you know, say you're drip fed data from the internet as an LLM, if you train on everything, probably it's going to not be very useful. And the other paper that I was going to do, which was another best paper at ICLR, was about selecting data, but it was incredibly theoretical, like way more than this. So I was like, I don't think I'll do that one, at least not for now. But yeah, that's the paper. I'll open it up for questions now. If anyone has any questions or anything.
I think I saw, just a comment on that vision. I think I saw in the appendix that the time they take, the method it takes, is more than one of the other methods, decision-based methods, but not substantially. So it's I don't know what it says, but you know, if they are trying to do it, it's just that they're more efficient than some of them.
Cool. We'll stop there unless there's any questions online. Let me just check.
Thanks, Peter.
If not, thanks everyone for coming.